morning. This is Schweitzer, and this is a little smartboard notes on basically half-lives. Half-lives are kind of an integrated rate law where we're looking to solve for a concentration um, at some time t. So anytime you're using integrated rate law, you should realize that we could have ourselves a zero order, a first order, or a second order. And technically, they each have their own equations, and we should be aware of those mathematical formulas to utilize them. So either way, you should not be really foreign to all those equations at this point. But either way, we'll see some as we move along. All right, so first things first, um, what is a half-life? Can I manually graph out, or in my head or with pencil math, a numerous half-lives in a row? So for example, 60 grams of A is reacting displayed above equation, half-life 15 seconds. How much mass left for 45 seconds? So the 60 in one half-life drops to 30, which drops to 15, which drops to 7.5, and it just keeps going in halves and halves and halves. And either way, this is going to be 15 seconds. This is now 30 seconds. This is now 45 seconds. So about 7.5 grams left. This is pretty commonplace and can shortcut a lot of problems to make them easier. And there we go. There's our particular math. All right, so estimate how much would be left after 20 seconds. Okay, now to do 20 seconds is going to be, you can estimate, all right, that 20, well, if this guy is 15, this guy is 30, so we're someplace in the middle here, and you should be able to get some rough estimate. All right. Now, in this case, at this point, we could only estimate that it is 30 grams, closer to 30 than 15. It's not a linear relationship, so keep that in mind. It's not right in the middle or whatever. So all right, let's move along. All right, so a couple of things we might note about this graphing. So in a half-life, is the rate changing? This is a good question, something that people don't always think about. In a half-life, is the rate changing? And the question is, look at the data provided. What is the order of this reaction? Again, this one is relatively straightforward. So we could say, well, at the mass of B, okay, so we're tracking the B showing up, or we could do A either way. I'm just going to change this to A. That's how we usually don't track that. Okay, so first at time 0, it's at like 60. And you'll notice that it just gets cut in half every time. So at this half-life, which would be 15 seconds, it's like right here. And then it's going to be like right here. And it's going to be like right here. And then it's going to be cut in half again. And we get this sort of sloping graph, something like this. So keep in mind that change in mass or change in concentration over change in time, this essentially, it is rate. So this is our most basic form of rate, the slope of the change in concentration, change in time graph. So you'll see the slopes, the rate starts relatively quick, but then slows down, slows down, slows down. So it's pretty common scenario. So is the rate changing? Absolutely yes. It starts out fast and slows down, and it is kind of exponentially slowing down. All right, so what is the order of the reaction? Now again, this is not something that we'll learn the first time here, but if you want to know the order of the reaction, we could potentially graph 3 different data sets here. Now, to do a zero order is concentration versus time. This is for zero order. For first order is time versus the natural log of the concentration. And time versus 1 over the concentrate. 1 over is the second order. So this is first order, zero first and second. If this is new to you, this particular idea, then you should watch a video out just straight up integrated rate laws. So we're going to make out three graphs. One is going to be concentration versus time, which is actually this guy right here. And we'll do natural log of the concentration versus time. And then we'll have another one that is going to be 1 over the concentration versus time. And this graph looks like this. Okay, this one will have a negative slope instead of a positive slope, but we'll get that in a second here. So how do I do this just on the fly? Well, what I would do is really the time is consistent here. The time's not really changing much. It's the same proportions. So what we want to do is we want to look and say, okay, how are my concentrations changing? We got obviously 30 units, then 15 units, then half of that. So this is getting smaller and smaller and smaller, which is not showing a linear proportion. So really, again, reminder of some things is we're looking for a linear relationship and a linear relationship. Now this is what reciprocaled here. So my graph reciprocals. It goes up. All right, so first things first, because of the rate of change on this guy, this guy, this guy, even before I graphed it, I would note this is not going to be a linear relationship. So the graph that gives me the linear relationship is the graph actually identifies the order of that graph. So then what I would do is I'd say, okay, well, look at this one here. What's the change here? What's the change here? What's the change here? Just some quick pencil math. You might note that we have about the same change in every single one of these guys. And then, of course, here you say what's the change here, 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 and you're going to find that this one is hooking like this. Okay, so the only one here that happens to be straight is this guy. So what's the reaction, since the 1 over the natural log of the concentration versus time graph is actually straight, then this guy is going to be first order. Okay, so again, the slope of the graph, all right, is my k. Keep that in mind. So if it were 0 order, the slope of this graph is k. The slope, again, here, because the slope's constantly changing, the k would be constantly changing. We know that's not the case. The k always stays constant for a given chemical reaction. So this one has a nice flat slope, and that slope is equal to my k value. All right, very important. That's multiple ways to calculate k. We want to be able to do that. Okay. All right. So again, here we have my data from the last guy, and this is the actual graph that matched up. All right. So what is happening? What is the rate constant for the reaction? Again, as I mentioned. All right. So the slope of this reaction is in fact the k value. So because it's first order, it follows the equation natural log of the concentration, right, equals negative kt plus the natural log of the concentration at, now, this is following a y equals mx plus b. That's now a straight line. This is the y-intercept, so it's plus our concentration, the natural log of our concentration at time 0. This is my y-intercept, and this is the time, and this is my k value right here. And this represents the slope. Okay, so here's two ways that you can find your k value. The k value never changes. It's the slope here on the particular graph that presents the order you're with. This is the first order reaction, and that's the k value. Is also initial rate. Initial rate equals my k value, concentration of A to the first power. And this is super important, that this is also the same k value. Initial rate, right? Now if I track this thing, mass of A over time, of course it looks like this. So this initial, that's not a very good graph, I did a better one earlier, but this initial rate right here is showing this guy right there. So anytime I want the initial rate, I would take some of my initial items, changes here, change in concentration over change in time, will give my initial rate. Get plugged into here, and there we go. Either way, now we have three ways of calculating the K value, either via the initial rate law and the integrated rate law for that order, or the actual graph, sloped. All right, and of course here now, there's the equation right here. What is the rate constant for this reaction? Okay, so now I talked about three ways in which we can get this rate law, but I'm going to go ahead and investigate an alternate way to do this. Okay, now we know this is first order, and even though the K does not change, all right, K not changing, we know that's the case. We know that my rate actually is changing. But what's not changing also is my half-life. My T1 half is not changing. So an easy way is they want a short, because it's so common, they want a shortcut way of doing this. So for this, to get my actual half-life, in order to get my K, to get my half-life, I could literally take my equation I have here, this guy, plug in a 60 in right here, all right, and then I could plug in my 30 right here, plug in my time, which is 15 seconds right there. So 30, 60, 15, and I can solve for my K value. That's a very common way of doing this. And regardless of what time, I could go, and again, this is concentration at, there you go. Just plugging in the values in here, I could use any time, any data point I want as long as I use the correct time. All right, so anyways, we're going to take with the numbers we plugged in here and just basically get this equation right here. No matter what, if I could put natural log of, let's say, okay, concentration at times T equals negative KT plus natural log of concentration of times original. This basically is 2 and 1. 30, and this should be 60 and 30. All right, this is the original, that's time T. So 2 and 1. So I'll show you the math that this 2 and 1 ratio always sort of comes out to the same. Now, I guess I don't have it there. So let's do this again here. Let's do it right here. So the natural log of 1 at time equals negative K T. I'm probably going to show up later in this thing because I know I did this, but natural log of the concentration, okay, times 2. All right, so let's solve this out to try and attempt to get this. This is on your laminated sheet. So I can change this into being natural log of 1 minus natural log of 2 equals negative KT. And then when I subtract these two guys, it's the same thing as doing, by rule of powers, natural log of 1 over 2, which is 1/2, which gives you negative KT. All right, and then natural log 1/2 is negative 0.693 equals negative KT. And then the negatives come off, and I get, this is the time for 1/2. Time for 1/2. All right, so this ends up just being a static formula, which is now I took the negatives off, and we just get our standard half-life formula. All right, so again, the K is not changing, the time half-life's not changing, so we can relate the two together. If you have the T half, you can find the K 1/2, the K for that particular reaction. Okay, so this is maybe a fourth way. Now this fourth way is really just the same equation, just shortcutted for a half-life. Okay, but make sure you note that important thought here is, and I'm sure it's going to come up again in this PowerPoint here, that this is only for first order. Okay, this is all first order, and everything that we've talked about as far as half-lives that you know of for how half-lives work is only first order. That's it. Everything you know is first order. That's it. Okay, so if you're going zero order, it's not going to work this way. If you go second order, not going to work this way. Only for first order, and that's real important. All right, so the most common scenario for half-lives is nuclear decay. Again, this is what we call a unimolecular system. So I have substance X simply breaking down into substance Z. Here's an example of this particular reaction. Again, it's a one item reaction where, okay, I'm not waiting for two things to collide. But keep in mind, for a unimolecular one-step reaction, we're going to always be first order. All right, so equals K value, concentration of X at, there we go. That's the rate law for this particular substance, which again, this guy's going to follow all the standard first order stuff. So natural log, concentration at times T equals negative K T plus 1/2, concentration at times 0, and of course, um, the the K value equals 0.693 over T 1/2. And of course, these two can get shuffled back and forth. All right, and it would also follow the natural log of the concentration at times T, and it should be a negative slope because of the negative value, and it should be straight. All right. All right. Again, all unimolecular items are going to be first order and one step. There you go. All right, this particular slide is once again going to reiterate how I got that formula. So I want to know how do I get this? So this is going to show us, you could pause this and re-look at it again. I've already gone over it, we'll do it again. Initial rate law, same K here as this K here. All right, plugging it in, rearranging algebraically, negative K equals the division of these two. All right, and of course, by rule of laws, I get this powers by rule of logarithmics. All right, and then there we go, plug in 2 and 1 here. Again, it wouldn't matter if I put 2 and 1, or I put in 10 and 5, or 200 and 100. It doesn't matter. You're always going to get a half, and you're always going to equal this. Okay. And then, of course, that simplifies this, which we have already talked about already. All right. Now again, bimolecular reactions. That would be like having two things coming together. Now again, this is not a nuclear type decay. This would be some other type of reaction. They do not follow this. And you can go ahead, you can try it. Plug in here, 2, plug in 1, and you're going to solve for a K for the half-life. You'll be able to solve for a time. Given the K, you could solve for the time for that particular process. All right. But if you went 200 and 100, you're going to get you're going to get the same K value because the K is not changing. K is temperature dependent, but you're going to get a different T1/2. Okay, so everything that you think about as far as half-lives do not work. Okay, they do not remain the same. The rate is still changing, but in the K the K only changes the temperature changes. So keep in mind the T1/2 will be changing. Okay. Now keep in mind as well here is that for a zero order, actually I don't think I have a zero on here. This might be the well, I'll come back to that in a second here. So what can we do with this reaction again? This is only for first order. Okay. So again, any kind of this is a recap. Traditional first order half-lives, given the quantities you can determine, given a half-life, K and half-life do not change, rate does change. Okay. Anyways, so that is the end of it. Let's just take a quick moment here and add one more small thing in here. Okay, be familiar with this page here. It's just a recap. Okay, what about zero order? So zero order is the concentration versus time. And it looks like this. Now, if it's zero order, then the concentration is not going to change with time. So either way, my K value is here, okay? My rate, so this K value is not changing, all right? My rate also is not changing. Sloppy there. All right. What about my half-life? Well, if before in the first order my K didn't change, my rate was changing, but my half-life did not. So here, since my rate's not changing, my half-life has to be changing. You can see that here, half of it's gone. Okay, and then now it took me X amount of time to get half of it gone. And now to get the next half gone, it's gonna be half of this. So this is now the half-life. In the same, so the time here took this amount of time to change, half of it. Now it's only taking half of the time. And then, of course, cutting this half again is taking half of that time. So in this case, my time for my half-life is constantly getting cut in half every half-life. So if it's the first one, if it takes 10 seconds for half to be gone, then because the rate's not changing, it's going to take only 5 seconds for half to be gone, then 2.5 seconds for half to be gone. Half-life is constantly getting cut in half. So again, just going back to the previous page, understand how we got this formula, why it only works for first order, and what are the ways you can calculate K. We also remember we're using rate law, all right, equals K, concentration of substance, let's say X or A, whatever we're looking at here, first order. This is the number of items in your rate determining step. So we're unimolecular, typically for first order. And this K value is the rate constant. Sometimes it's thought of as the effectiveness of the reaction, or even collisions if need be, although first order doesn't have that. So this is proportional to your rate, although it's not your rate entirely. All right, thank you very much.